Plastics are everywhere, and for good reason. They're durable, cheap, and incredibly versatile. But they also have a huge flaw. Their production and disposal are environmental nightmares. This is where exciting new research from Canadian scientists at the Dalhousie University comes in. Virtually all plastics are made from fossil fuels like crude petroleum and natural gas. These materials consist of long chains of hydrocarbons, molecules made of hydrogen and carbon. The process starts with refining, where crude oil and natural gas are converted into ethane and propane. These substances are then subjected to a process known as cracking, in which high temperatures break down their molecular bonds, transforming them into ethylene and propylene. These molecules form the building blocks of most plastics. In the final stage, known as polymerization, these molecules are chemically bonded into long chains, creating various types of polymers, the scientific term for plastics. But we all know that fossil fuels are not sustainable, whether they're burned for energy or processed into plastic. Here's a startling fact, for instance. By 2050, greenhouse gas emissions from plastic could be as much as 2.8 billion tons a year. That's equivalent to the emissions from 615 large coal plants. Although the exact timeline is fuzzy and progress is not nearly as fast as we'd like to see, the complete phase-out of fossil fuels is inevitable. We simply have to if we're to preserve both nature and human civilization. But herein lies a problem. How would we make plastic then? It sounds like a problem that's too far into the future. But forward-thinking researchers at Dalhousie University are looking to tackle it today. Their solution? You're breathing it right now. They found a way to make alternative plastic materials starting from atmospheric nitrogen, which they've trapped into molecular cages.
What we've found is that we can use nitrogen molecules from the air. And that's the most abundant resource we have in our atmosphere. It's like 78% nitrogen. There's so much of it that it's very little is productive. Like humans don't use, it's basically a carrier gas. And we thought that if we could find a way to harness it, then we could really harness like a very untapped resource. The issue being that usually when people condense nitrogen, it's for the purpose of making explosives. They're very unstable. And we had to try and find a way to stabilize the nitrogen if we want to really make plastics out of it. So I found a way to use phosphorus, which is an element that people usually don't think about in the periodic table. It's not a classic element. It's part of the P block. And we found a way to use these phosphorus reagents to trap these nitrogen molecules in cages. And it turns out in this cage that everything ends up being quite stable. You can get a lot of nitrogen molecules in a cage, and then you can even put the nitrogen molecules together. So you can put the cages together. And that forms the basis of plastics. So once we make this material, we can then make plastic films out of it. We can make these like hard little plastic pieces. And we found that because we're not using traditional elements, these also have some benefits that plastics don't have. Like they're biodegradable, and they're actually also flame retardant. So if you light it up, you try and burn it, the plastic film itself, it just chars on the outside. So you can imagine you could use this in applications where you have a lot of plastic, which is typically flammable. If you need to have it in like a space exploration device or something where you typically use a plastic, this could act as a substitute and it could be a little bit safer in that application. I mean, we've done a lot of testing about what the materials properties of these things are, but one advantage of them is that there are so many different ways you can make these plastics that are available to us as chemists, that like the opportunity to tune the properties of these plastics, like we barely scratched the surface. I mean, right now we can make them hard, you can make them very fragile, you can make them very brittle, you can make them like you can stretch them and deform them and it will retain the shape. But we have yet to like really see where we can go with this. Originally we were motivated because we were trying to find a way to deal with a problem that people are going to be facing, which is as we try to divest from fossil fuels, which of course we need to do as a society if we want to have a real future. The problem we're going to come up against is that we also get those fossil fuels also provide us the building blocks for our materials. So all the plastics come from petrochemicals, which are derived from fossil fuels. Like 85% of all the plastics we make And plastic's really great. Like it's going to be very, very hard to not use plastics because they just do so many things so well. I think the first challenge we had was when we were trying to make the materials. No one had ever made anything like this. So when we were trying to figure out what we had, because originally it all starts in like a beaker or a little vial. And when you make your material and it's in this little vial and you're looking at it and you're thinking like, okay, like, no one's ever made this. I don't know how I'm gonna figure out what it is. The initial challenge, I spent a lot of time, looking at all the data and trying to figure out if I had what I thought I had. And there was a moment when I realized I guess you could call it a eureka moment a little bit, but I realized what the thing I was doing kind of almost by accident that was making the actual polymeric material, making the thing that would become the plastic. And it was a feeling of, like, I ran to my supervisor like they show in the movies, and I was like, hey, I think I've been doing this reaction this way because we had a piece of equipment that wasn't working, and the whole time was giving us what we wanted. We looked back in the data and we thought, oh my God, we have it. And then from that on, when I first made the plastic, I wasn't expecting it to be what it was. I was expecting it to be kind of a brittle, like something you could snap with your fingers. And it wasn't like that at all. Like, it was this stretchy film. And I was like, this is just like plastic. I had a colleague actually who made another film like that. He was testing it. He was trying to see if he could decompose it using certain methods. And that's when he found out that you can light a flame to it and it doesn't even burn. So from that point on, like, everything about this material surprised us, and we think that there are a lot more surprises in store. So right now we kind of have two classes. So we have one that biodegrades, that if you put it in the right environment, it will just decompose to its components, which are the components of fertilizer, so phosphates and nitrates. The problem with that is that you don't want to have too many phosphates and nitrates in the environment. So we need to look at the impacts of that and how we can control, if there are ways we can control how it degrades more effectively. One of the more exciting things is the idea of adding it in small quantities to other plastics or to other materials, like sustainable materials. Because one aspect of the cages is that they make these very, very rigid rods. And if you can think about the way people add rebar in cement when they're when they're building big concrete structures, you need the rebar to reinforce it. One idea we have is using this as like kind of a molecular rebar, so reinforcing other materials, seeing if we can if we can take advantage of this very unique molecule that we have that's present in all these polymers. First, the nitrogen we get from the atmosphere, it first has to be converted into ammonia, because that's how it becomes very reactive. And nitrogen to ammonia conversion is it's like maybe the most important chemical reaction we have, because it's the ammonia we use for all our fertilizer that's allows us to go to the supermarket in January and buy ripe oranges. So this is also a key part of our process, is that we're able to, because ammonia is just used for fertilizer typically, but we try and harness it to use materials. So we take the ammonia, we have these phosphorus reagents we've developed and these reactions that we've developed that make these cages very efficiently. And then once you make these cages, you're then able to polymerize them using some less, I wouldn't say less traditional, but without the use of a catalyst. It happens very easily at room temperature. You don't have to use elevated temperatures. So in that sense, you cut some big costs of usual manufacturing, which is having to heat your reaction. So we're able to make these very, very efficiently and very, very quickly, which is also important. In terms of scaling up and mass production, the engineering side of this is something that I'm less familiar with, but you have to consider like mass transport, how your material mixes. Right now our material, when you mix it, it becomes very viscous, which means that you are going to have to use a lot of energy to stir it and keep it you have to keep it in solution. So that's something that's the problem in the future that we'd have to tackle with like the help of some process engineers. And I think in terms of scale up, our biggest challenge would be finding a way to get that nitrogen from the air to ammonia so we can use it in our chemistry in green and efficient ways. So right now in Nova Scotia, where I'm from, there are 2 big green nitrogen facilities have been proposed and approved for design, and their aim is to use renewable resources to fuel that reaction that converts nitrogen into ammonia. So we're really interested with a partnership there, forming an alliance where we can use our chemistry for better use.
Joseph, who has a background in polymer and inorganic chemistry, emphasizes that it all started as fundamental research. It was only later that Joseph and his supervisor, Dr. Saurabh Chitnis, who initially dreamed up the project, were awed by the potential practical applications.
It is a very forward-thinking premise. I mean, the idea is, right now it's still, I would consider it fundamental research. At least that's how it started. So when my supervisor thought about, initially came up with this idea, and when he was funded for it, it was a very, very fundamental idea. It was the idea of just trapping nitrogen in these cages and then combining them. But we didn't consider initially the impact that we'd be having on the environment and the fossil fuel industry as a whole. It wasn't something that we had initially thought of until we kind of looked at them again and we're like, well, these are actually solving a really big problem in our society if we think about it. The project was dreamed up by my supervisor, and I got lucky to come in at the ground floor on this research. So I owe a debt of gratitude to him, as well as the people at Dalhousie who sent me here.
This peer-reviewed research into alternative plastics is just the beginning. It's a story of science, innovation, and a hopeful future for plastics. That's all for today, folks. If you found this story as fascinating as we did, don't forget to like, share, and subscribe for more science news.